Hello there, and welcome to this collections of notebooks and tutorials on advanced digital signal processing. This is a course offered by Professor Schuller at the Humanities University of Technology. I am Renato, and this notebook is about frequency warping and minimum phase filters. Let's get started. We start this notebook with an example, and in this example we want to design a warped low-pass filter with cutoff frequency of 0.5 times pi, where pi is the Nyquist frequency. So here we have half the Nyquist frequency, and here this frequency is the end of the passband with frequency warping close to the Bark scale of human hearing. Before we do this, for a comparison, we'll design an unwarped filter with 4 coefficients with these specifications. So here we are importing SciPy signal, we are importing matplotlib to plot, and here we are using the Remez algorithm. Note that the Remez is normalizing to sampling frequency equals to 1, and here we will have our Remez filter. So this is the unwarped filter coefficients calculated with the Remez algorithm using these specifications here. So 0.5 pi is the cutoff frequency. We have here the coefficients. We can take a look at the frequency response. So using SciPy FracZ, so we're plotting here the frequency response of these unwarped filter coefficients, and this is the frequency response. We can see that this is not a good filter. The passband is too wide and there is almost no stop band attenuation. So this filter is probably useless for our application. So next step, we will design the FIR low-pass filter of 4th order, which we then want to frequency warp in the next step with a warped cutoff frequency. So first thing we need to do is we have to compute the all-pass coefficient for our all-pass filter, which results in an approximate Bark warping. So this equation here comes from this paper, Bark and ERB bilinear transform. So it's equation number 26. You can download this paper from this link here. And here Fs is the sampling frequency in kilohertz. And then we need to use this for our warp design. So what we're doing here now, we have this warping phase. This produces a phase for an all-pass filter. It takes as an argument the input vector of normalized frequencies from 0 to pi and the all-pass coefficient. So the all-pass coefficient is calculated from this equation here that you find in this paper. You can download here. You can read and see is equation number 26. So we are defining here this all-pass coefficient. Then we are calling this warping phase, and we have our warped cutoff frequency. Then we need to normalize to 2 pi to use with the Remez algorithm. So we're doing here, and now we are calling the Remez algorithm with this new cutoff frequency that we calculated after all these procedures, and we have these filter coefficients in the warped domain. Here A is the warping all-pass coefficient, FCW is the warped cutoff frequency. Then we normalize the cutoff frequency to 2 pi. We have here use this the input for the Remez algorithm, and it gives us the filter coefficients now in the warp domain. So this is the frequency response of this new filter. So we are once again using FracZ from SciPy. Here, this is the filter we obtain from the C coefficients if we don't replace the delays by all passes. Here we can see that in the warp domain we obtain a reasonable low-pass filter. So in the pass band from 0 to somewhat above 1.6, it has a drop of about 10 dB, and in the stop band we obtain minus 30 dB attenuation, which is much more than before. but it might still not be enough for practical purposes. So now we use the same coefficients, but now we will replace the delays in the FIR filter with all-pass filters. So in this way, we go from frequency response HZ to H warped of Z. That will be the H of all-pass filters given by this equation here, and it will look something like this. So what we do is we have here the warping all-pass filters. We have the numerator and the denominator. We'll calculate the impulse response. X is the impulse response. Now we will have our warped delays. So we will take this X and we will filter with this numerator and denominator using the whole filter from psi pi signal. So we will have y1 here, then y2 will be the y1 filter with this numerator and denominator. We have y2 here, and then we will have y3, and then the output of the warped filter, it will be the C0 times X plus C1 times Y1 plus C2 times Y2 plus C3 times Y3. So this is the procedure we had before these coefficients C from here, filter coefficients in the warp domain, but now we are replacing the FIR delays by all passes. So what we're doing, we're defining here the warping all pass filters, and then we are doing this X times C0 plus Y1 times C1 plus Y2 times C2, and here is our all pass filters. Then the output is given by this, the sum of all these, the Y of n, and we can see the frequency response of this filter now, and this is the frequency response of our final warped low pass filter. We can see again that we have a drop of about minus 10 dB in the pass band, now from 0 to 0.05 pi, and the stop band attenuation of about 30 dB, which is somewhat reasonable. We can see the impulse response of this filter here if we plot the Y out, we compute it from here, and it looks like this. This is the resulting impulse response of our warped filter. What is most obvious is its length. Instead of just 4 samples as our original unwarped design, it easily reaches 80 significant samples, but it's in principle infinite in extent. So this is also what makes it a better filter than the unwarped original design. You can take a look at this paper which I mentioned before, and also a paper by Professor Schuler, Frequency Warping in Low Delay Audio Coding, and you have good examples and explanations of this type of design. We reach now the minimum phase filters. So remember linear phase filters, its phase function is linear. We have the function phase minus capital omega times d with a group delay of constant d. So the impulse response of linear phase filters have the property of being symmetric around some center. So for example, these are the filter coefficients in warp domain from previous example, and we have 4 sample impulse response starting at 0, and we have a symmetry at around 1.5. Hence we have a constant delay of the system of 1.5 samples. Another example of a linear phase filter is a piece of a sinc function. So this FIR filter has a constant delay factor of d equals to 5. So the delay factor D is in the center of the impulse response, and we can factor it out from the DTFD of the symmetric impulse response. So this is the frequency response, goes from 0 to 2 times D. The impulse response, we factor out the center exponential. So we factor out the center exponential. Then we know that the impulse response D minus N is equal to impulse response D plus N. So using this, we will get this equation here. And then if we replace exponentials by cosine, we have this expression here, and hence the phase is minus D times capital omega. So we show that any symmetric filter has a linear phase and that the center sample corresponds to the signal delay. So this is what we've seen here and also here. This was how to prove. So we factor out the center exponential. Now, instead of also going from 0 to 2 times D, we go from 0 to D. We know that this part of D minus N is equal to D plus N. And then we get to this equation here, and we take the phase as the angle. Then we find this result here. So we can plot its zeros in the complex plane of the Z transform. So here we have this function to plot poles and zeros. And here we have this plot. So this is the sinc function, the part of the sinc function here. We are plotting the poles and zeros on the complex Z-plane field, the imaginary part, and we observe that the zeros near 1.9 and near 0.5 and on the unit circle. Its zeros are computed with the command roots we used here, and their magnitude with ABS. The magnitude of the zeros. So here we can see that we have 1 zero at location 0 and 1 at infinity, and 6 zeros are on the unit circle. We have 1 at distance 1.93 from the origin and 1 at distance 5 10 times to minus 1, which is the same as 1 divided by 1.93. We can see here we have the Z-plane, the zeros. Here we have magnitude of the zeros. We have here this one. This one is a location distance 1.93 from the origin. And we have this one here, which is 1 divided by this. So as for those 2 zeros, we have 1 zero inside the unit circle at distance r and 1 outside the unit circle at distance 1 divided by r. So we are talking about these 2 zeros here. So linear phase systems and filters have the property that their zeros are inside and outside the unit circle in the Z domain. For stability, only poles need to be inside the unit circle, not the zeros. But if we want to invert such a filter, for example, for equalization purposes, the zeros turn into poles, and the zeros outside the unit circle turn into poles outside the unit circle, making the inverse filter unstable. So this is a problem that we have. To avoid the instability of the inverse filter, we define minimum phase filters such that their inverse is also stable. So this means that all their zeros need to be inside the unit circle in the Z domain. We can write all linear filters as a concatenation of a minimum phase filter with a null pass filter. So we can see here, this is the frequency response of a filter. We can write, if it's a linear filter, we can write as a concatenation of a minimum phase filter with all pass filter. So this can be seen from a hypothetical minimum phase system, H-min, which has all its zeros inside the unit circle. So now we can multiply it with an outpass filter such that its poles coincide with some of the zeros of the minimum phase filter inside the unit circle. These poles and zeros then cancel, and what is left is the zeros of the outpass filter outside the unit circle at a reverse conjugate position 1 divided by A if A was the position of the original zero. In this way, we can mirror out zeros from inside the unit circle to the outside. The magnitude response does not change because we used a null pass, so there's a magnitude 1 for mirroring out the zeros. As a result, we have a system with the same magnitude response, but now with zeros outside the unit circle. So assume we would like to equalize or compensate a given transfer function, for instance from a recording. As we saw above, this transfer function can be written as the product of a minimum phase filter and all pass filter. So only the minimum phase filter has a stable inverse. Hence, we design our compensation filter as 1 divided by the frequency response of the minimum phase filter. If we apply this compensation filter after our given transfer function, for instance from a recording, we obtain the overall system will be our frequency response times this compensation filter, and the overall transfer function now is a null pass with a constant magnitude response and only phase changes. You can also refer to the excellent book Discrete Time Signal Processing by Oppenheim. How can we obtain a minimum phase version from a given filter? We basically mirror in the zeros from outside the unit circle. So take our above example of the piece of the sinc function filter. So we see the zero at 1.93, which we need to mirror in. So we neglect the zero at infinity, which comes from starting with a zero sample. To achieve this, we first take the z-domain polynomial of the impulse response and cancel that zero by dividing by the polynomial with only that zero. 1 minus 1.93 times z to the power of minus 1. Fortunately, we have the function deconvolve, which is identical to polynomial division. So to do this, we are importing SciPy signal. We are using the deconvolve function, and it will return b and r. So r is the remainder. In our case, it's practically 0, which means we can indeed divide our polynomial without any remainder, which we expect since the 0 we divide by was in the polynomial, so that we can always factor it out. After that, we can multiply the obtained polynomial b with the 0 inside the unit circle at position 1 divided by 1.93 by multiplying it with the polynomial with only that 0. So 1 minus 1 divided 1.93 times z to the power of minus 1. So here now we are using this convolve. B comes from here. And then we have here the H-sync C MP is now our minimum phase version of the filter. So this is what we did. We had here the roots, and then we use the deconvolve H-sync 1 and minus RT1. So this here, it will give us the polynomial b and remainder r, and then we are multiplying, convolving the b with 1 and 1 minus 1 divided by RT1 conjugate, which is this part here. And we get our minimum phase version of our filter. So we can take a look at the impulse response. It looks like impulse response of the minimum phase filter, and observe that our filter now became non-symmetric with the main peak at the beginning of the impulse response. The resulting frequency response is obtained with this frac-C. So we're plotting the frequency response from the impulse response we obtain here for the minimum phase filter, and this is the frequency response of the minimum phase filter. Now if we compare the above frequency response of the minimum phase with the linear phase plotted here, we can see that the magnitude is about the same, except from an offset of about 5 dB, which is not so important because it's a constant gain factor. But looking at the phase, we see that the minimum phase has less phase lag. This is the minimum phase, and this is the linear phase. So looking at normalized frequency 1.5, we see that the linear phase filter has a phase lag of about -7 rad. So at 1.5, so no, this is the linear phase, so 0 -7. Whereas the minimum phase has a reduced phase lag of about -5 rad. So 3 -2, so -5 rads. If we take the derivative of the phase function to obtain the group delay, we will get correspondingly lower values, which means that the minimum phase filter will have less group delay than the linear phase filter. In fact, it has the lowest possible delay for the given magnitude response of the filter. So if you have a given magnitude filter design and you want to obtain the lowest possible delay, you have to take minimum phase filters. Also observe the phase drop around points. They are not always at plus or minus pi, but in other cases where the magnitude has zero crossing, where the phase is not well defined. So a convenient SciPy function to obtain a minimum phase filter with a similar, not exactly the same magnitude frequency response of a linear phase filter is this SciPy signal minimum phase. So here you can take a look at the help function. So it takes some arguments, it returns the minimum phase version of the filter. And as an input, it expects a filter with the square desired frequency response, which we can obtain by convolving the linear phase filter coefficients with itself. So in our example, an approximate linear filter is obtained by if we convolve H-sync with itself, and then we get this, we call this minimum phase function from SciPy with this squared, so it's this convolved by itself. And when we plot the frequency response, we have here the magnitude looks the same, but the phase looks different because it starts at 0 instead of pi as before. And this is because the filter coefficients here have a switch sign, and this is no problem because we can always change the sign by multiplying the filter or its output by -1. So when we compare the coefficients by looking at them, we see that the coefficients are similar but have indeed opposite signs.